very much. Yes, so a complete shift now. Clean technology, raw materials. Going to concentrate a little bit on some carbon figures to try and fit this meeting, which is why I've acknowledged particularly some of my colleagues at CSM who work on such things. And what we're coming back to is a slide here that Karen Hanghoy showed yesterday. We're coming back to these patterns that as we move into renewable energy, if you like, as we go from an age of fossil fuels, we're going into the age of materials. And not only will we need to mine more of all of the major metals, but we're using a wider range of elements than we've ever used before. And you can see here on this very nice diagram from Volker-Sepp that this is the elements used in energy pathways, and by now we're up to the majority almost of the periodic table, and that's particularly in our clean technologies. Now, I haven't got time to go through all of those, so I'm going to concentrate on my own particular favourites, which are the rare earth elements, as just one example of these kind of elements. And if I wanted to be really trendy, then I guess I should go for lithium or cobalt, because these things go very much in fashions. But I'm going to stick with the rare earths and show you why. So rare earths then, and clean tech, all the low energy lighting that we have requires rare earths. For the oil industry people here, they're very important in the cracking catalysts for the petroleum industry. They're making the speakers in your mobile phone work. They're in every computer in the disk drives. So they're all around us in lots of applications, including some very clever things in medicine and luminescent paints and all kinds of new technologies, but often in very small quantities. So our headlines for today are the use of neodymium, because we all go in fashions and headlines, and for clean tech then, decarbonisation, it's about electric cars. So that's what's driving people at the moment. In order to drive one of these cars, you need some kilograms of neodymium in a neodymium iron boron magnet, which makes the drivetrain the best motor in these electric cars. So not in batteries, where everybody's racing to, cobalt and lithium, but you still can't drive one of these without another funny metal, and that's a neodymium in these very strong permanent magnets. And if that's kilos of rare earths, people seem to have forgotten about this in rare earths, but for tons of rare earths, then it's about these big wind turbines on land and particularly offshore. So to get about 3 megawatts of a direct drive motor is about 2 tons of rare earth magnets. So in these very large ones, then you're up to tons of neodymium iron boron magnets. And so that's driving the use of rare earths up as we need these clean technologies. Okay. So what's the problem then? As we need more of these, can't we just go out and get them? And of course, this is the problem that you will have heard of with these specialty metals. It's often because we really don't overall need very much. So 150 to 170,000 tons of rare earths each year is all we need, going up to, say, 250,000 tons. That's 100 times smaller than the amount of copper that we use. Okay, so this isn't of interest to Rio Tinto or Anglo American or the big companies. And it is of interest, though, and has been for a long time, to China, who've on purpose developed their rare earth mines. They happen to have some very nice deposits. And on this map of the mines here, you can see the concentration over here in China. And a few years ago, apart from Indian mineral sands, pretty much the concentration would have been there, and I would have said over 90% of rare earths, 95% are coming out of China. In the last few years, we now have a brave mine at Mount Weld in Australia, processing in Malaysia, and the figure's going down now 85 towards 80%. But that figure is held only really by one major operation at Mount Weld. There's a little bit of stuff happening in Russia, and there's a very famous mine over here in America, but I'd like to highlight the trend that's happening now in the world as us geologists and our colleagues are bringing mines online. What's happening to that stuff? Well, over in America, they're digging up the bastnasite ore from the Mountain Pass mine, and then, yes, it's going on a ship, and you can guess where that's going, is over here to China. It's part owned by Shenzhou rare earth resources who are better at processing and can do it more cheaply than anyone in the USA. And so the supply chain is being concentrated here in China. And a very important point for all of these specialty metals, I don't think China have a real big deal on the mining of rare earths. We need to put ourselves in our place. It's that supply chain that they want to dominate, making rare earth alloys, making rare earth magnets, making electric vehicles, making wind turbines, making low energy lighting, all of these things. And by having the mines and that first part of the supply chain, that's exactly what they're very clever at doing. This applies to all our specialty metals. If we really want a piece of the high value action, as Karen showed yesterday, then we need to make sure that we've got secure supply chains right from the mining source. Okay. And of course, it's that business about having things that are economically important, so important for all the things I said and for electric vehicles and wind turbines and things in the case of rare earths, but possibly vulnerable to supply disruption. China can do what it likes and it's difficult for us to complain. Then that's what makes things, on that graph, puts them into this critical box. And that's what we mean when we say critical raw materials. It is actually a technical term, and it means that those things. It doesn't just mean important, it means that it's also vulnerable to supply disruption. Okay. So that would be my number one thing about rare earths, and vulnerable to supply disruption. Now let me do responsible sourcing then, because this is a very nice graph that Roscoe gave to me that I don't think you will have seen before. So here's China and its legal supply, and this big hump that you might be familiar with is filled up with illegal mines. So not only have the standards in China for environmental performance been much lower than anywhere else, they know that, they're trying to sort that out, but it's very difficult for them because a lot of their production is being smuggled out illegally. And this is Mount Weld and the rest of the world at the top. Okay. So that's the second thing then. If we're interested in clean technologies, hadn't we better be interested in having clean raw materials at the front of our supply chains? And when we say clean and responsible sourcing, I could go on at length about all the things that a responsible mine has to do, but because we're about decarbonising, I thought I'd go to these figures for kilograms of CO2 equivalent and carbon footprints of these things. And here's the whole periodic table, but maybe we just look at 1.5 for iron and 8.2 for aluminium. And then here's my friend neodymium in those magnets. It's 17.6. So if I was a manufacturer looking at this, I might think that rare earths aren't perhaps such an environmentally friendly thing to go for. And I think even as geologists, I'm going to show that we need to be joined up with the kind of ways that manufacturers will be thinking. Because then when they do a complete LCA of a car or something, they'll be taking these kinds of figures, and we better be sure where they're coming from. So I've got 3 roles then for geoscientists here. One, that criticality business, help establish secure chains outside of China, and that could be for rare earths and anything else. Help achieve responsible sourcing, okay, deposit types, which are the best ones, the most environmentally friendly. So there's an expense in terms of environment, remember, as well as cost. But there's no premium today, I'm pretty sure to say, for responsibly sourced raw materials. You can't charge 20% more because this is a very nice mine, so you have to compete on cost as well. And my third thing here then is to link up to the value chain and talk the same language as manufacturers. So if they're going to look at carbon footprints and those kilograms of CO2, then perhaps we'd better be mindful of that too. So on number 1 then, on exploration, well, there's no problem. I think the next but 1 talk's going to tell us this as well. There's loads of rare earths in the world. All these spots, you don't need to worry about what they are, just worry about the fact or be pleased that there's lots of them. And they're lots of different colours because there's lots of different sorts of deposits. So we know about rare earths enriched in the crust in lots of different places. But the clever thing is which ones fit that bill of being economically possible and environmentally the best ones to go for. Okay. So all looks good then. We know lots of different deposits. Here's a Roscoe graph that shows production going up and interestingly use not going up so much. So beware of these specialist raw materials. If we're using more renewables, maybe fewer rare earths are going into cracking petroleum catalysts. And so actually, it isn't a picture of huge amounts of rare earths being needed in the future. And wouldn't that put off investors? And yet we need that neodymium. So the picture is always quite financially complicated. And with 15 elements in the mix here, even worse than normal. And here's my star player, neodymium. In fact, that's the one where supply will really be squeezed. Whereas we're going to have oversupply, all these things below my deficit surplus line on this Roskill graph, will be in oversupply. So that's going to be problematic for miners as well. And why is that? It's because of geochemistry. It's a real geological problem here. And on this graph, I've got the size of the rare earth cation. So this is a real piece of geology, geochemistry coming in here, versus the rare earths here. And this you may remember from geochemistry. You might use it in some geology as the lanthanide contraction. And in nature, all these rare earth cations are pretty similar in size. So these Chinamen, because remember that most rare earths are coming out of China, they go round together. There's no such thing as a neodymium-only deposit without loads more of lanthanum and cerium. Okay, so that's why the supply graphs are complicated too. And although we might separate these Chinamen from these Chinamen in nature, individual ones are never found. So what we have to be interested then in exploration is not just finding rare earths, but much cleverer than that, finding the right rare earths in deposits. So deposits that will match the demand. And here's some figures for demand. And if you just look at the kind of size of the colors on the pie chart here's that American one that's now being shipped to China. And maybe we're not so bothered because there's far too much cerium in that carbonatite deposit at Mountain Pass, and not really enough neodymium and no yttrium. It's really light rare earth enriched, to use the jargon. The Mount Weld one that's holding its own against China is a little bit better. And we've been working on one at Songwe Hill in Malawi, which is actually, if you just compare the colours in that pie chart with the colours over here, quite a good match for what's predicted to be the current and future requirements for rare earths. And that's why this company, which is a British company actually, are still in business exploring in Malawi, because they can sell the very nice profile of their rare earths. Okay, so I dared to show you some rocks, because I don't think we've seen many rocks in this conference so far. This is a carbonatite. It's an igneous rock made of at least 50% carbonate. And why does that deposit work? It works because it has a complex mineralogy. Here's a nice cathodoluminescence picture of apatites. You see there it has this apatite, and it has another funny rare earth mineral called synchazite you won't have heard of before. And when we put them together, this is a normal profile in a rare earth deposit, and this apatite is rather abnormal, all moved and hydrothermally altered rare earths. And together, these two minerals produce that very nice balance. So that's where it is with exploration for us, is really understanding these igneous and hydrothermal processes in detail and being able to forecast where companies should be exploring, even when they know where the deposit is. How do they maximize the return in terms of finding the right rare earths? And so here's a Horizons 2020 project, this normal kind of project diagram. And if you imagine the work that's been done on copper or diamonds or iron ore, we're nowhere near that kind of stage in understanding any of these minor tech metals. So in rare earths, we've got a long way to catch up with the major players. And in this project, one thing we're doing is trying to make a mineral systems approach. So we're using some of the oil industry exploration and trying to apply that in rare earths. And then going to some of the old classic textbook diagrams. This is a geomodel, nice one, from Mike Labar in '77. And then bringing them up to date. So we're needing to visualize these exactly like Mike Labar did in 1977 from that experience, but adding in all the geophysics techniques that we can use now that we know, adding in vectoring, like people have done loads of work on porphyry coppers. How can we apply that around rare earth deposits? And applying process mineralogy. It's not just good enough to know that things are in the rock. How will they perform when they go through the processing plant? That's essential now. What will the environmental aspects be when these things are on the waste tip? How much energy will it take? How much water will it take? All of that needs to go into our geomodels. And we're even reaching through to the social aspects of these deposits into the models. Okay. And so if we have to do all of that for the things we know on land, can I just throw in for 3 seconds, the one that hits the BBC telly and everything all the time is whenever the Japanese do something on their deep sea muds with rare earths. There might be something for the next speaker to think about how realistic it is to hoover rare earths at 5,000 parts per million off the seafloor, 4.5 kilometers below the surface, when you really need to have done all the things I had on the other slide, and we don't know that yet on the land. So maybe these things are a long way off, but I'd be interested to discuss that. So just to stay with processing then, so with our ones on land, we're looking all the time at what is the most efficient and environmentally friendly forms of processing. And you see there are lots of stages of crushing and grinding and then separating the minerals and then dissolving them up and then splitting the rare earths from each other. And some deposits, like this one here, I'm going to come back to in a minute, they don't need all this crushing and grinding. They can go straight through to this dissolution stage to go on to separate the rare earths. You can easily pull these rare earths in these. They're called ion adsorption deposits, coming back there in a minute. So they're on a kind of motorway. Because there's a paradigm in mining that the energy, the real big energy, is the stuff used to crush and grind rock. Something like between 2 and 6% of all the world's energy, people say, is used in crushing up rocks on mines. Okay, so that's the thing that we try to avoid. So these deposits should be really nice. Okay. And so here are 4 different sorts of deposits. Mineral sands, like beach sands, where all the titania comes from that we use. Carbonatites, like that one at Songwe Hill. Alkaline rocks, one of the world's wackiest chemistry in rocks, and then our ion adsorption clays. And the point I want to make here is they all have positives and negatives in terms of responsible sourcing. There is no single perfect rare earth deposit. We could get our rare earths now as much as we like outside of China, but in these mineral sands, which are being mined already, of course, the minerals are radioactive, and that's the biggest social problem with rare earth deposits. Nobody wants to know about those radioactive minerals. So the rare earth ores, if you like, are put back in the ground in Australia and South Africa and all the other places they're being dug up. Carbonatites we've already seen, they tend to not have enough neodymium, so we need to find the right ones of those. There's a lot of processing work. This has never been done commercially in a lot of these alkaline rocks. And here, these are our ion adsorption ones that I said could be very nice because we don't really need to do any crushing and grinding and complicated separating. The rare earths are literally sitting on the surface of clays, so they adsorbed onto the clay surface, and then we can just leach them off. And that, we think, should be very environmentally friendly until we look at the life cycle assessment of these deposits. And we see on this graph here, collated from a number of papers there, Bryan Lovell is the big hard rock carbonatite-related mine in China. And if you just look along the figures, you'll see compared with ion adsorption clay, there isn't much difference. So actually, from the manufacturer's point of view, if you wanted to know about global warming potential, you wouldn't automatically go for these. So our geology view is opposed to an LCA view. And the reason for that actually is this paradigm about crushing and grinding is fine if you're producing copper concentrates or something on a mine and shipping them away. But for rare earths, the real big problem is the chemicals that you use to dissolve up the minerals. They don't go off to a smelter for pyrometallurgy. They're often dissolved on the mine. And those chemicals are used in ion adsorption clays just like the others. And that's what we need to be mindful of. What energy embodied in chemicals is coming into a mine and how is that used? Okay. And so then even when we've done all of our geology, it depends on what power sources you're putting in. And here's a mine in Africa, and if it uses and this is all the stages along that first chain of rare earth production. And just look at the orange bars are really small, and that's the hydroelectricity that they have in that country at the moment. But they don't have enough hydroelectricity to power industry. So if they get things like this mine started, they can't possibly keep their lights on as well as doing this. So they're going to have a very low grade coal power station, and if this mine uses that, it immediately goes from being a very environmentally friendly rare earth producer to being the worst, highest global warming potential rare earth producer in the world, even though it would be very important economically for this country, becomes very environmentally unfriendly. And so this company is now going back and it's changing its energy mix and bringing in some more renewables and energy storage to try and make itself look environmentally friendly, as well as helping development in that country. And we can produce these kind of graphs as well. So on here, we've gone for all of the life of mine up to 45 years, looking at the grade of rare earths that are being produced and what the global warming potential is from each stage, right? And the point I want to make here, that this is not an operating mine. This is in geologists' territory. These figures have been produced from a pre-feasibility study. And when you go through the stages of exploration, these studies are usually, for a listed company, publicly available information. So anybody can get hold of this information and start to assess a project and its global warming potential and all its other environmental aspects right from that exploration stage. And so that's normally geologists, that's normally us running those early stages. And we can, if we're interested to put this kind of thing in, be thinking right from those first stages about even the global warming potential of that deposit that we're working on, because the kind of processing is already published in those reports. So here's my conclusion. Sorry, it's a bit long. This is what I sent off as my one slide. So, yes, I hope that I've shown that rare earths, other minor elements, are essential in lots of our low-carbon technologies, and we're using a wider range of elements than ever before. And so there's a challenge for geologists to keep pace with what the technologists are using. We need to be ready when they need it. How can we be actually ready with it? And it's about more than just the straightforward exploration. We need to think about responsible sourcing, about mineral processing and the environmental impacts, and to link up with the manufacturers to produce the kind of figures and the kind of deposits that they'll actually be looking for, such as in that LCA incorporation. So for rare earths and the headlines, the neodymium, and what we want from manufacturers in return, of course, is lots of new uses for cerium and lanthanum, so that we can go for all of the rare earths, because those other rare earths will be in plentiful supply. Thanks very much.
Well, you left us in no doubt this is a Geological Society meeting. Thank you for bringing us back to minerals. Time for a couple of questions from the floor. Yeah.
When you were talking about supply and demand at the start, we're always told, especially rare earths when it's on the news, you know, population's increasing, technology, more and more technology. So why is it then that the gulf between demand and supply is, or seem to be growing, and is that to do with like circular economy and reuse of materials, or is there other factors at play there?
So in that graph, Roskill, we're bringing on some new sources. So, Yes, so there were some new sources coming on, which of course are needed for neodymium, but as they produce more neodymium, they produce even more lanthanum and cerium, and that's what's creating the oversupply on that graph.
Francis, why do you assume that a lignite power station has to emit CO2 to atmosphere?
Oh, because I'm 100% confident that the idea is that it will emit CO2 to atmosphere. That's why.
Okay, all right. Well, I mean, it's just always the problem with life cycle analysis. Everybody seems to be looking backwards and then caring about things that nobody cared about when they were doing all of the other sort of contributions to that life cycle analysis. And if anybody cared, they could cut the emissions significantly from all of those.
But isn't that?
And indeed, if you're looking for deposits and you're considering CO2 emissions, then deposits that are near CO2 storage would probably be a good idea.
But isn't that exactly the point, that in that country they're not going to put any kind of CCS on their power station, but they are going to use that coal power? So that's maybe a whole other subject to discuss, isn't it?
If you think that the USA and China are ever going to be serious about climate change and not make sure that all other countries are going to be equally serious, whether they like it or not, then I think that's unrealistic. So, we've seen graphs of people going to net zero globally, and we're not going to do that and let any country take a free ride. They'll get a rock dropped off their main station transformer.
Okay, we'll leave it as a hanging
Yes,
challenge.
I think.
Okay, one more in the middle, and then we'll take our tea break.
Do you foresee it being economical to mine old landfills to get some of these rare earths back from previous used goods? The old phones, the old things to get it. Can it be done?
Mining old landfills, I doubt it very much at the moment, to be honest. Recycling more, absolutely. Magnets are the things that in time will be the easiest ones to recycle. But I don't think we're going to go urban mining into old landfills just for rare earths. I don't think that's realistic.
No, it wouldn't be economical.
Yeah, no, because they're not that expensive.
Yeah, okay.
These things, when you say critical, it all sounds very glamorous, but it doesn't mean to say that they cost a lot of money at all.
But the recycling is quite important. I mean, the electronic component recycling.
Yes,
That's quite a big business.
Well, I think it goes without saying that anything that we dig up,
Yeah.
we should be holding it in use as long as possible and then recycling it. And some of the things like those huge wind turbines should be easy.
Spence PGS. So they're producing potentially a spectrum of rare earth elements alongside the things that they're really interested in. I'm just wondering what happens to all this byproduct containing things that could really be potentially useful in the future. Is that safeguarded in some way?
That's a really good question. I always have this vision of things like a little pot of thulium or something alone and unloved in a warehouse somewhere. and that is actually the case with some of them. But there are, the industry also moves a little bit. So a low value use, say, of cerium is polishing powders. And when the price went up, people jumped out of polishing powders. They could use something else. So they go and substitute if they can. So I guess when the price comes back down, then maybe other uses can come in. And it's a point to say these will be available so that people can come in and use them for other things as well.
Okay, we'll leave the rest hanging for discussion and coffee break. Thanks.